Everyone. First of all, I can see that there are people from all over the world, so good morning or good afternoon, depending on where you are. So let's start the webinar with the first lecture by Dr. Miguel Gallardo. So Miguel serves as the secretary of the clinical embryology section of the Portuguese Society of Reproductive Medicine and treasurer of the Cryobiology Interest Group of ACELIR. Additionally, he is a lecturer in the master's program in human reproduction at Universidade de Lisbon de Portugal. Today, Dr. Gallardo will talk to us about the basic principles behind ultrafast protocol. So please, Dr. Gallardo, the floor is yours.
Thank you, Andre. Very kind presentation. Hello to all the attendants to the webinar. Thank you very much as well, Kitazato, for the invitation. I see that you are loading my presentation now. So, as Andre said, my aim here today is to talk about a little bit the biophysical principles behind these shorter protocols, ultra-fast vitrification, rapid elution protocols, and get a bit into why they work. So in the first slide, we have the true protagonist of the webinar. We can go to the next one. It's just the human oocyte. I guess most of the audience are embryologists, so probably you are with me when with a shared admiration for this cell. No? There are many fun facts about this cell, the biggest one in the body, as far as I know. It's very old as well. It forms during embryogenesis, and when the woman is born, it's already there, so it's going to be with us for many years until eventually it's going to grow and mature. It's a process where it is going to accumulate a lot of nutrients, and it has a lot of organelles and biochemical machinery to support the fertilization and the early embryo development. So it's awesome cell, but that complexity that comes at a cost, and is that post-ovulatory oocytes are going to age very fast. For them to hit the homeostasis, the balance, let's say, the biological balance, is very costly. So the cytoplasm is going to be only functional for so long, and we need to cryopreserve them and do so with much care so we avoid damaging these very delicate structures. So how are we going to do that? If you want to move on. Yeah, no, this is the picture before. You can see that how it's going to look inside the oocyte. We said it has a lot of components, a lot of stuff going on inside, but still only 20% of those molecules, solutes, organelles are the oocyte, and we have a lot of free water inside. And that, if we move to the next slide, it's going to be a problem when we are trying to do the cryopreservation. Probably we know this. In the next slide, we can see that a lot of water means that once that we try to reduce the temperature of the system, it is cool, the energy is going to leave the system, and the water molecules are going to search for a more stable, lower energy configuration, which is why they form the ice. And if it forms and it grows inside our cells, it's going to lead to cryo-injuries and eventually cell death. There's only so much ice, intracellular ice formation that an oocyte can tolerate. So the less, the better. So to avoid this ice formation, we need the classic second-order phase transition that we all know and love, which is the vitrification, glass transition. If you go to the next slide, you will see that a simple solution, this is a classic image by Lieberman, that a saline solution, if we expose it to our typical cooling agent, which is the like in nitrogen, is going to turn opaque. This is because it's telling us that the water molecules in that solution have formed the crystalline structure, and that's what we want to avoid in the oocytes. How are we going to do that? Well, we have a clue about that in the drop of solution in the right. We have added cryoprotectants such as ethylene glycol and DMSO, and disaccharide such as sucrose. So once if we expose that cryoprotectant solution to the liquid nitrogen, it's going to remain transparent, meaning that it is solid now, but the water molecules have not formed ice. And that's what we're going to do inside the oocyte. So how do we do that inside the oocyte? In the next slide, we can move there and see the classic graph of vitrification. How it's going to work. So we have the concentration of the solution or the system, in this case, the system is our oocyte, and the temperature. And if you click, we will see that the oocyte is sitting, as we discussed before, around at 20 to cool, to go down in the y-axis, the temperature axis, at that concentration of 20%, we have to go through the melting temperature area where ice is going to form. It's a matter of time. So we have to cross that dangerous region as fast as possible. So that's why, if you can click a couple of times, you will see that the pioneers in vitrification realized that we need to artificially increase the concentration of solutes in the oocyte by getting CPAs, cryoprotectants inside, and removing water. And only then we could, with the cooling and warming rates achievable, go safely to the glass transition temperature. And once we do the warming, we do the elution part, the rehydration part, and these components, the cryoprotectants and the water, move through the plasma membrane. This is the part of the vitrification protocol that we are going to talk about today in this webinar. It's not the cooling and warming, but how we can prepare and how we can recover the cells from before and after the cooling and warming. So let's take a look into that. It's a matter of an osmotic exchange, as we said before. And typically, this is going to look like we expose the oocyte to the equilibration solution. And if you, for example, if you click a couple of times, and there we can see that in the Kitazato protocol, for instance, we do that gradually by exposing this equilibration solution to a basic solution. But all the same, we expose the oocyte to permeant cryoprotectants that's going to enter the cell through the lipid plasma membrane. And we're going to remove the water, and that is helped in the vitrification solution by an even higher concentration of cryoprotectants, plus the addition of non-permeant cryoprotectants, such as saccharose or trehalose. Once we do that, perfect, we can cool and warm, and afterwards is where we are going to remove the cryoprotectants and reintroduce the water in a controlled fashion, and the solutions with a decreasing amount of non-permeant cryoprotectants are going to help us do that. If this all sounds a little bit too abstract, we can move to the next slide, and we can see that actually. We don't need to imagine it. When we cryoprocess an oocyte, we will see it under the stereo microscope, under the inverted microscope. We can see how it behaves. And if we happen to record it, and we extrapolate the volume based on the area, we can plot a very nice graph and see the osmotic behavior of the oocyte. And in the next slide, we will see that that is what was done by pioneers in vitrification in the decade of the 90s and the early 2000s. Very, very important work was done to determine the permeability of the oocytes to different cryoprotectants in different conditions, different concentrations, and all that knowledge has allowed to arrive to the current protocols. And not only that, but furthermore, in the next slide, we can see how once we know the permeability characteristics of the oocytes, we can use it to predict the flux of water on the permeant CPAs, such as ethylene glycol and DMSO, through the plasma membrane of the oocyte. And by passive diffusion, for example, in the equation that is there, might look a little bit frightening, but it's just a differential of the volume of water during time, and is determined by the negative of the hydraulic conductivity of the membrane, by the area of the oocyte, the constant, and the temperature, and the differential in osmolarity, in intracellular and extracellular osmolarity. It's a simple equation that we can solve. And if we put that into a model, that's very helpful because we can simulate many conditions. Instead of doing the experiments in the lab, we can now do it in the computer, and we can iterate very fast. It's very helpful, especially when we are talking about human oocytes that are very scarce, very hard to work with. So it is this set of tools that the group I was part of in the civil engineering school, we built a model based on the parameters that have been previously estimated by other authors. And it shows that the oocyte in the solid line is gonna shrink very fast when we expose it to equilibration solution. And after 10 minutes, it's gonna do the same. Yeah, let's remain in that slide a little bit more. In the previous one, it's gonna do the same in the vitrification solution. And the intracellular molarity of the oocyte, which is in the dot line, is gonna rise very fast, supposedly. So, from a mathematical point of view, it makes sense to say, okay, let's take only those two parts of the protocol and join them. Maybe in 2 minutes, the oocyte should reach the target intracellular osmolarity, which we must remember is what is going to determine whether it achieves vitrification or not when it's cool and warm. So if it's the same, it could work. But the next step is then to look at this video of the oocytes, because the model maybe doesn't take into account some limitations of the oocyte. The permeability is not so high under real conditions and so on. But we can see that this is an oocyte that is exposed to non-vitrification solution. So is this the first left part of the graph? And as predicted, it's gonna shrink quite fast during the first minute of exposure. And after that first minute, it's really reaching a stable volume, which will recover if we allow it more time. But in this case, no, we expose it to the vitrification solution, and we can see that as predicted by the model, it shrinks even more to a stable degree. So in the 60 seconds of vitrification solution, it shrinks even more. And it's here when we will load it into the cryotop, or our vitrification carrier of choice. So apparently the behavior corresponds to the reality of the model. But still, we needed to do, we did, some proof of concept in human oocytes and abnormally fertilized zygotes that were donated for research. And we obtained, in a very small sample size, because it was a very pilot study, good survival, meaning that the biophysical principles that we model do work, so it's good news. And not only it survives, but the zygotes seems to have the same ability to do the first cleavage, at least. So we know that the biological machinery inside is not fully compromised, at least. But it was a very initial validation that we did in 2018. So since then, if we go to the next slide, we'll see that we had the standard protocol that was, it is being used for decades. Then there was this proposal to shorten the time of equilibration. It was replicated in 2021. That year as well, it was reported by the group of man that maybe on the elution part, the rehydration after warming, we could only expose the blastocysts in this case to 1 minute of thawing solution, and that will be enough. And that was followed up by the group of Lieberman, where they tested and gathered a lot of preclinical and clinical evidence of the feasibility of this short protocol on that side of warming as well. So I would say nowadays, both in the oocyte model, I want to highlight the group of Dr. Mitchell Hsu in the United States, as well as the work by Embryo Tools by Nuno Costa Borges. There is work in the preclinical and clinical validation of all these configuration of protocols. And I think that's what my distinguished speakers that are going to follow after me are going to talk about. So I'm not going to go into that anymore. But as we see, the protocols, there is the possibility of big change. And just to finish, what were the perils, the cons, possible cons of potential problems of these short protocols? I mean, we would be afraid of ice formation, but based on the technical validation, we can see that if it survived, there wasn't much ice that formed. There could be membrane damage by increased osmotic flow. We could be concerned about higher degree of shrinking because there is higher mechanical stress, or the less free water content that is achieved could compromise the viability of the oocytes at a later stage. So those are things that have been addressed. I think we will see later, but it has potential benefits as well. I want to finish in a positive note because not only, of course, it's very obvious for everybody that logistically it will be more convenient, but it's also a simpler protocol. Less manipulation, it's more automation friendly than that's coming in the future. We have to think about the oocyte as well. The time it is exposed to suboptimal conditions in current protocols, because we spend a lot of money in the best incubators, very fast ICSI, and so on. And then for the cryopreservation, they stay for a very long time in suboptimal temperature and osmolarity. So this reduction probably can be positive for them. And the last point is that maybe a different protocol of the standard, I don't know in which shape or form exactly, but if we are achieving a lower cell volume, a lower free water content, we could reduce the ice forming tendency of the oocyte. So it is possible that we can even achieve more consistent results. I don't know about blastocysts, but especially in oocytes, because in donor we get 90% survival. When we are talking about patients, maybe we go even lower. So there is room for improvement, and I'm looking forward to see what's coming next. And that's all. Thank you very much. That's from the Civil Engineering School, where this work was developed. And obrigado from Lisbon, is where I am now.
Well, thank you very much. Great presentation, Dr. Gallardo.